There is a sentence sitting inside the equations of quantum electrodynamics, the most rigorously tested theory in the history of physics, and it says something that should not be allowed to be true. It says that an antimatter particle is mathematically identical to an ordinary particle moving backward through time, not similar. Identical. Richard Feynman proved it. Physicists have used it to predict real experimental results for 80 years, and nobody has ever found a way to make the sentence go away. That is not science fiction. That is the working mathematics behind every particle collider on Earth. And it means that somewhere at the smallest scale of reality, time does not seem to know which direction it is supposed to flow. Tonight, we are going to follow that crack all the way down. We are going to sit inside a laboratory where physicists built a machine that sends information backward along its own timeline and watched it work. We are going to meet a mathematician who handed Einstein a birthday present in 1949 that quietly terrified him, a solution to Einstein's own equations describing a universe where flying in a big enough circle could land you in your own past. We are going to watch the paradoxes that once made backward time travel look logically impossible get dissolved, one by one, using nothing stranger than thermodynamics. By the end of tonight, you will understand exactly why so many serious physicists have quietly stopped saying this is impossible and started saying instead that we do not yet know what stops it. Get cozy. Hit subscribe if you're new here, because the line between past and present is about to get a lot thinner than you were expecting when you pressed play. It is the spring of 1940, and Princeton is quiet the way university towns are quiet at night, when the undergraduates have gone to bed and the only lights left burning are in the offices of people who cannot stop thinking. John Archibald Wheeler is one of those people. He is a young professor, already known for a restless, almost childlike willingness to entertain ideas other physicists would be embarrassed to say out loud. And on this particular night, an idea has been circling in his head for weeks, refusing to leave. He picks up the telephone and calls one of his graduate students. The student's name is Richard Feynman, and he will go on to become one of the most important physicists of the 20th century. But right now he is 22 years old, and he is used to Wheeler calling him with strange questions at strange hours. This one, though, is stranger than most. Wheeler asks him to consider a single question. What if there is only one electron in the entire universe? Not one electron per atom. Not billions of trillions of electrons scattered across every star and every living thing. One electron. A single particle that exists at one moment, vanishes and reappears somewhere else, doing this so many times, so quickly, weaving forward and backward through the fabric of time itself, that from our vantage point it looks like uncountable trillions of separate particles, all with exactly the same mass, exactly the same charge, exactly the same properties down to the last decimal place. Wheeler pointed out that this would explain something genuinely strange about electrons, something physicists had simply learned to accept without asking why. Every electron in the universe is perfectly identical to every other electron. Not almost identical, not extremely similar, identical, in a way that no two handmade objects in the macroscopic world ever are. If there were really only one electron, weaving through time like a needle through cloth, that would explain the identity instantly. Of course, they are all the same electron. They are the same electron. Feynman did not dismiss it. He did the thing that separates a great physicist from an ordinary one. He took an idea that sounded like something out of a physics department drinking game, and he sat down and tried to work out what it would actually mean, mathematically, for a particle to travel backward through time. Here is where the story stops being a curiosity and starts being something you should sit up for. When you write down the equations that describe how an electron moves through space-time, the deep mathematical machinery underneath quantum electrodynamics, you find that the equations are, in a very literal sense, indifferent to the direction of time. This is not a quirk. It is a structural feature of the physics. Run the clock forward in the mathematics and you get an electron, a particle with negative charge, moving from the past into the future in the ordinary way you would expect. But take that same electron and instead of moving it forward through time, run its trajectory backward. Do not change anything else. Just flip the arrow. What comes out of the equations is not nonsense. It is not an error term that needs to be thrown away. It is a fully consistent, physically sensible description of a real particle 1 with exactly the mass of an electron, but with the opposite charge. Positive instead of negative. That particle has a name. It is called a positron. It is antimatter. And here is the detail that should genuinely unsettle you, the detail that took decades to be fully appreciated even by physicists who worked with this mathematics every day. This is not a metaphor. It is not physicists reaching for poetic language to describe something they do not truly understand. In the formal apparatus of quantum field theory, a positron moving forward through time and an electron moving backward through time are the same mathematical object. The equations cannot distinguish between them. There is no experiment, even in principle, that could tell you which description is the real one, because they are the same description viewed from two different temporal directions. Feynman built an entire technique out of this observation. Physicists today still use what are called Feynman diagrams to calculate the outcomes of particle interactions, and in those diagrams, antimatter particles are conventionally drawn as ordinary particles with an arrow pointing backward in time, not because it is a convenient shorthand invented for classroom simplicity, because it is formally correct. When two physicists calculate the probability of a particular collision happening inside a machine like the Large Hadron Collider, some of the terms in their calculation are, without any exaggeration, particles travelling backward along the time axis, contributing to a result that always, without exception, comes out moving forward, the way the rest of the universe expects it to. This idea has a formal name in physics, CPT symmetry. It states that the laws of physics remain unchanged if you simultaneously reverse three things at once: the charge of every particle, the spatial orientation of every interaction as if reflected in a mirror, and the direction of time itself. Flip all three together, and the equations governing the fundamental interactions of the universe do not notice the difference. This is not a fringe hypothesis floating at the edge of theoretical physics. It is one of the most rigorously tested symmetries we have. It has survived roughly 70 years of increasingly precise experiments designed specifically to break it, and it has never once failed. Every serious theory of particle physics we currently possess is built with CP symmetry baked into its foundations, because every attempt to build a theory without it has produced predictions that contradict what we actually observe in nature. Sit with what that means for a moment, because it is easy to let a sentence like that wash past you without feeling its weight. The deepest, most successful, most exhaustively verified framework we have for describing the behavior of matter at the smallest scales treats the forward flow of time as one equally valid option among two. Not the only option, not even, in some formal sense, the preferred option, just one branch of a symmetry that is exactly balanced by its opposite. You were taught, the way almost everyone is taught, that time has a direction the way a river has a current, that it flows from past to future, that this flow is one of the bedrock facts of the universe, as fundamental and unshakable as the existence of matter itself. And in your everyday experience, that is completely true. Eggs break. They do not spontaneously reassemble. Coffee cools. It does not spontaneously heat itself back up by pulling warmth from the room around it. You remember yesterday. You do not remember tomorrow. Every single one of these observations is real, and none of them is in dispute tonight. But none of those observations comes from the fundamental equations describing particles and forces. They come from something else entirely, a statistical tendency, a large-scale behavior that emerges from the collective motion of enormous numbers of particles, a concept physicists call entropy, which we will spend real time with later tonight, because it turns out to be the hinge on which almost this entire story swings. At the level of a single particle, at the level where quantum electrodynamics does its work, that statistical tendency simply does not apply. Down there, forward and backward are, as far as the equations are concerned, two names for the same kind of motion. Wheeler's phone call to Feynman did not ultimately convince the field that there is truly only one electron looping endlessly through spacetime. There are subtle reasons that specific version of the idea runs into trouble. Reasons involving how many positrons we would then expect to see in the universe compared to how many we actually observe. But the phone call left something behind that mattered far more than the specific hypothesis. It left behind the observation, verified again and again in the decades since, that the mathematics underlying antimatter is, quite literally, the mathematics of particles moving backward through time. Physicists did not go looking for time travel and stumble onto antimatter as an accidental consequence. It happened the other way around. They went looking for a consistent description of antimatter, the kind confirmed in cloud chambers and particle detectors and hospital PET scanners around the world every single day. And buried inside that description, they found backward-flowing time waiting for them, uninvited, uncomplaining, and mathematically inescapable. This is where our story tonight actually begins. Not with a philosopher's daydream, not with a screenwriter's convenient plot device, but with a working piece of 20th century physics so well established that it now sits inside your undergraduate textbooks, tucked into a corner most people never think to examine closely. A sentence, hiding in plain sight, that says the universe, at its smallest and most fundamental level, has never been quite as certain about the direction of time as we are. And once you know that sentence is there, you cannot help but ask the next question. The question this entire episode is going to spend the night chasing. If the smallest pieces of reality do not seem to care which way time points, what would it take at a larger scale, at the scale of a spacecraft or a laboratory or a human life, to make that same indifference show itself? What would it actually take to walk backward through the door? That question has an answer, or at least the beginning of one, and it comes from a mathematician who did not set out to build a time machine at all. He set out to give his friend a birthday present. In the spring of 1949, Albert Einstein turned 70 years old, and in the tradition of academic communities everywhere, his colleagues at the Institute for Advanced Study in Princeton decided to mark the occasion with a collection of essays written in his honor. Physicists and mathematicians from around the world contributed short, respectful pieces reflecting on the man and his work. It was meant to be a celebration, a gesture of gratitude, the kind of thing that gets bound into a leather volume and placed on a shelf. One of the contributors was a quiet, intensely private mathematician named Kurt Gödel. You may already know Gödel's name from somewhere else entirely. In 1931, at the age of 25, he had done something to mathematics that mathematics has never fully recovered from. He proved, with total rigor that any formal system powerful enough to describe basic arithmetic will always contain true statements that cannot be proven true within that system. Mathematics, in other words, cannot ever fully close its own books. There will always be truths sitting just outside the reach of proof. It is called the incompleteness theorem, and it did to the foundations of mathematics roughly what Einstein's relativity had done to the foundations of physics. It revealed that something everyone had assumed was solid ground was, underneath, considerably stranger than anyone had wanted to admit. Gödel and Einstein were, by this point in their lives, close friends. They walked together most days at the Institute, deep in conversation, two of the most formidable minds of the century strolling across a quiet American campus, discussing whatever happened to be on either of their minds. Einstein reportedly said, late in his life, that his own work no longer meant much to him, that he came into the office chiefly for the privilege of walking home with Gödel. So when Gödel sat down to write something for his friend's 70th birthday, he did not write a warm personal reflection. He did something far stranger and far more Gödel. He picked up Einstein's own field equations of general relativity, the equations that describe how matter and energy curve the fabric of space-time, the same equations that had already reshaped Einstein into the most famous scientist alive, and he asked them a question nobody had thought seriously to ask before. He asked what would happen if the entire universe were rotating. Not a galaxy rotating, not a planet rotating, the whole universe. Every particle of matter in existence, spinning slowly around some common axis, the way a child's top spins on the surface of a table. Standard cosmology, both then and now, assumes the universe as a whole has no meaningful rotation, that when you average over the largest scales, everything settles into stillness. But Einstein's equations do not forbid a rotating universe. They simply describe what one would look like if it existed, and Gödel, being Gödel, was not going to let an unexplored corner of Einstein's own mathematics go unexplored. He worked through the equations, region by region, and produced something known today as the Gödel metric, an exact solution to general relativity describing a universe filled uniformly with rotating matter. And buried inside that solution, waiting for him, was something that should not have been possible according to almost everything physicists believed about the structure of cause and effect. In Gödel's rotating universe, space-time itself gets twisted by the rotation, the way water in a bathtub gets dragged into a spiral by the drain. Physicists call this frame dragging, and it is a real, measured, experimentally confirmed effect even in our own non-rotating universe, produced on a much smaller scale by spinning masses like the Earth. But in Gödel's model, the twisting is so severe, so total, that it does something extraordinary to the paths available through space-time. It becomes possible, mathematically, for a sufficiently determined traveller to plot a course accelerating along a specific curving trajectory using nothing more exotic than a powerful enough rocket that would carry them all the way around, through space, and back to the exact point in time from which they departed. Not a similar point, not an earlier era in some general sense, the identical moment. The traveller would step out of their spacecraft and find themselves shaking hands with the version of themselves who had just climbed in. This is what physicists call a closed time-like curve, a path through space-time that loops back on its own origin. And Gödel had shown with full mathematical rigour, using nothing but Einstein's own equations, that general relativity permits such loops to exist. Not as an approximation, not as a numerical curiosity that vanishes if you calculate more carefully, as an exact, internally consistent solution. Einstein's reaction when he read it was not celebration, it was something closer to quiet alarm. He wrote, in his own reply included in that same commemorative volume, that Gödel's result had presented him with an important problem, one he had not been able to resolve when he first formulated the theory of relativity, and one that continued to trouble him. Einstein did not believe our actual universe was rotating in the way Gödel's model required. And every subsequent observation, the extraordinary uniformity of the cosmic microwave background above all, has supported him on that specific point. But that was not really Einstein's worry. His worry was more fundamental. He had built a theory whose own internal mathematics permitted time travel under the right conditions, and he could find no clean, principled way to write those conditions out of the theory. The door was not open in our universe, but the door existed. His own equations had built it, and he could not find the mathematics to lock it. Gödel, characteristically, did not seem especially troubled by any of this. Later in his life, in conversations recorded by people who knew him, he expressed something closer to intellectual satisfaction than alarm. If time travel into the past is logically possible, he argued, then in some sense time itself, the ordinary common-sense notion of time as an objective flow from past to future, cannot be treated as a fundamental, unquestionable feature of reality. It has to be, in some sense, an illusion, or at least a feature that depends on the specific structure of the universe you happen to live in, rather than a universal law binding every possible universe equally. Gödel, remember, had already spent his career proving that mathematics could not fully certify its own foundations. It should perhaps not surprise us that he found a certain grim consistency in discovering that physics could not fully certify the flow of time either. Now, it would be easy, and it would be wrong, to walk away from this story thinking that Kurt Gödel proved time travel is real. He did not. He proved something narrower, and in some ways more unsettling, that the theory of general relativity, the same theory that correctly predicts the bending of starlight, the precession of Mercury's orbit, the existence of black holes, and the operation of the GPS satellite currently telling your phone where you are standing, does not, on its own, contain any rule that forbids closed, time-like curves. The theory is silent on the question. It will describe a rotating universe with time loops just as faithfully, just as accurately, as it describes our own quiet, non-rotating one. Whether such loops actually exist anywhere in physical reality is a separate question. One general relativity alone cannot answer. That gap, the space between what the mathematics permits and what nature actually allows, is where an enormous amount of the physics we are going to spend tonight exploring actually lives. Because Gödel's universe was not the only solution physicists would eventually find containing closed time-like curves. Over the following decades, other theorists working through Einstein's equations in other contexts, studying other exotic configurations of mass and energy, kept stumbling onto the same uncomfortable feature: a rotating cylinder of infinite length, certain configurations of wormholes, certain regions near a spinning black hole. Every single time, the mathematics kept whispering the same thing. It is not forbidden. It is merely difficult. And that distinction, impractical versus impossible, is going to matter enormously as tonight goes on, because it is the exact hinge on which one of the most serious debates in modern theoretical physics still turns. Stephen Hawking, decades after Gödel, would become convinced that the universe must contain some deeper principle, some cosmic safeguard, actively preventing these loops from ever fully forming in reality, even if the equations technically allow them on paper. He would eventually go so far as to test that conviction in one of the strangest experiments any physicist has ever conducted, an experiment involving a party, an empty room, and an invitation sent out only after the party was already over. We will get to that party. But before we can understand why Hawking felt he needed to defend the universe against its own mathematics, we need to understand something even more immediate. Something happening not in some exotic rotating cosmos, and not in the abstract language of a 70-year-old mathematical proof, but in ordinary clocks, on ordinary aeroplanes, in the ordinary sky above you tonight. Because before anyone can meaningfully talk about travelling backward through time, they first have to reckon with something physicists have already proven beyond any reasonable doubt is happening to you constantly, quietly, in one direction only. You are already a time traveller. You have been one since the moment you were born. And the proof of that fact is going to be the thing that makes everything else tonight feel less like fantasy and more like the next entry in a very long, very real scientific ledger. That is where we are going next. Before we go any further into wormholes and rotating universes and paradoxes, we need to stop and build something solid underneath all of it, because everything else tonight depends on you trusting one foundational fact completely. That fact is this. Time dilation, the idea that time itself can pass at different rates for different observers, is not a hypothesis. It is not a theoretical possibility awaiting confirmation. It is measured, verified, and quietly built into the infrastructure of modern civilization, whether you have ever thought about it or not. Let's start with something almost absurdly ordinary. Commercial aviation. In October of 1971, two physicists, Joseph Hafele and Richard Keating, decided to settle a theoretical question using nothing more exotic than 4 atomic clocks and a stack of commercial airline tickets. The clocks were cesium beam devices, the most precise timekeeping instruments available at the time, capable of measuring intervals down to a matter of nanoseconds. Hafele and Keating strapped 2 of these clocks into passenger seats and flew them eastward around the entire planet on regularly scheduled commercial flights. Then they flew 2 more clocks westward, all the way round in the opposite direction. A 4th set of reference clocks stayed exactly where it was, ticking quietly at the United States Naval Observatory in Washington, D.C. Before takeoff, they had already done the math. Einstein's special relativity predicts that a moving clock ticks more slowly than a stationary one, an effect called time dilation. Einstein's general relativity predicts something that works in the opposite direction. A clock at higher altitude, in weaker gravity, actually ticks slightly faster than one closer to Earth's surface. Airplane travel involves both effects simultaneously, moving fast and flying high, and depending on which direction you fly relative to the Earth's own rotation, those 2 effects combine differently. Hafele and Keating calculated, in advance, exactly how many billionths of a second each set of flying clocks should gain or lose relative to the ground clocks. Then they flew the experiment, landed, and compared the results. The clocks that had flown eastward had lost time relative to the ground, just as predicted, drifting by tens of nanoseconds. The clocks that had flown westward had gained time, drifting the other way by a larger margin, again matching the prediction. The agreement between calculation and measurement fell well within the experiment's margin of error. 2 ordinary commercial jets had just become, without any special equipment beyond 4 suitcases full of atomic clocks, a working demonstration that time is not the same everywhere. It literally ticks differently depending on how fast you are moving and how deep you sit in a gravitational field. That experiment is now more than 50 years old, and the evidence for time dilation has done nothing but grow stronger and more precise since. Consider the system sitting quietly in your pocket right now, the one your phone consults every time you open a map. The global positioning system depends on a constellation of satellites orbiting roughly 20,000 kilometers above the Earth. moving at around 14,000 kilometers an hour. Those satellites experience both relativistic effects at once. Their speed causes their onboard clocks to run slightly slower than clocks on the ground, exactly as special relativity predicts. Their much weaker gravity at that altitude causes their clocks to run slightly faster, exactly as general relativity predicts. The two effects do not cancel out. When you add them together, the net result is that GPS satellite clocks gain roughly 38 microseconds every single day compared to clocks sitting on the surface beneath them. 38 microseconds sounds like nothing. It is not nothing. If engineers had not built a correction for exactly this effect directly into the GPS system's firmware, the timing errors would compound every single day, and the positioning data your phone relies on would drift by an accumulating margin of roughly 10 kilometers daily. Within a week, your phone would be confidently routing you to the wrong neighborhood. Within a month, it would be routing you to the wrong city entirely. Every single time you use a mapping app to find a coffee shop, a road you have never driven before, or your way home in the dark, you are relying silently and completely on a real-time correction for the fact that time itself does not pass at the same rate for a satellite as it does for you. This is not an isolated party trick confined to satellites and jet planes either. Physicists have pushed these measurements down to genuinely startling scales of precision. In 2022, a research team working with an optical lattice clock managed to measure gravitational time dilation across a vertical separation of just 1 millimeter, roughly the thickness of a credit card. They lifted one part of the clock apparatus by that single millimeter relative to the rest of it, and the two halves of the same clock, sitting almost on top of each other, disagreed with one another by precisely the tiny amount Einstein's equations predicted. Your head, right now, lying on your pillow, is aging at a measurably different rate than your feet. And then there is the experiment that took this out of the world of laboratory instruments entirely and put it into a human body. In March of 2015, NASA astronaut Scott Kelly launched to the International Space Station for what would become an almost year-long mission, orbiting the Earth at roughly 28,000 kilometers an hour. Scott Kelly happens to have an identical twin brother, Mark Kelly, who is also a NASA astronaut, and who remained on the ground for virtually the entire mission, going about an ordinary life while his brother circled the planet overhead. When Scott finally returned to Earth, NASA had, without needing to design any new experiment at all, one of the cleanest natural tests of relativistic time dilation ever available to science, two genetically identical human beings, one of whom had spent nearly a year moving at orbital velocity. The result matched Einstein's prediction exactly. Scott had aged very slightly less than his brother over the course of the mission by a margin of roughly 8.5 milliseconds. Mark Kelly, with the dry humour astronauts tend to have, joked publicly about the difference, noting that where he used to be simply a few minutes older than his twin, he was now a few minutes and several milliseconds older still. 8.5 milliseconds is a genuinely tiny number. You could not feel it, notice it, or measure it with anything short of extremely precise laboratory instruments. But it is not a metaphor, and it is not an approximation. Scott Kelly's body, at the level of its atoms, its cells, the number of times his heart physically beat over that mission, experienced measurably less elapsed time than his brother's did, because he spent that year moving fast enough in a weak enough gravitational field for the effect to become real and quantifiable. There is an even more extreme example sitting in the career of a Russian cosmonaut named Sergei Krikalev, who has spent a cumulative total of more than 800 days in orbit across multiple missions throughout his career. Add up all of that orbital time, and Krikalev has accumulated a total time dilation of roughly 20 milliseconds relative to everyone who stayed on the ground his entire life. He is, in the most literal, technical sense available to physics, the most time-displaced human being alive, 20 milliseconds younger than he otherwise would have been. He will go to his grave, decades from now, a fraction of a second behind the rest of us, carried there quietly by nothing more dramatic than the ordinary physics of orbital velocity. Now push this thought experiment further, because the effect scales dramatically as you approach the speed of light, and this is where the real strangeness of forward time travel starts to show its teeth. Imagine, hypothetically, a spacecraft capable of reaching 99.5% of the speed of light, something wildly beyond our current engineering, but nothing relativity itself forbids. A traveller aboard that ship, journeying outward and back, might experience only 5 years passing according to their own body, their own clock, their own sense of time. Meanwhile, back on Earth, roughly 50 years would have elapsed. The traveller would leave at 30 years old. They would return, by their own experience, having lived only 5 more years. And they would step off that ship onto a planet that had aged half a century in their absence. This is not speculative fiction. This is the direct, experimentally verified consequence of equations that have never once failed a test in over a century of increasingly precise scrutiny. Forward time travel, in other words, is not a question mark hovering at the edges of physics. It is settled science, as solid and unglamorous in its own way as the boiling point of water. It happens to you right now at an imperceptibly small scale every single second of your life. The differences accumulate quietly. You are, in the most literal sense available to physics, a time traveller already, moving into the future at a rate ever so slightly different from everyone standing near you. Which raises the far more interesting, far more unsettling question this entire episode exists to chase. If the equations of relativity allow this much flexibility moving forward, why should they draw a hard, uncrossable line the moment we ask about the other direction? For most of the 20th century, physicists assumed exactly that whatever strangeness relativity permitted going forward, the arrow simply could not, under any circumstances, be persuaded to point the other way. That assumption held firm for decades. And then, in the middle of the 1980s, an astronomer trying to write a novel picked up a telephone and called a physicist at Caltech with a question that would quietly begin to unravel it. That phone call is where we are going next. In the middle of the 1980s, the astronomer Carl Sagan was doing something a little unusual for a man who had spent his career as one of the most recognizable scientific communicators in America. He was writing a novel. Sagan, host of the landmark television series Cosmos, a professor at Cornell, and by that point, arguably the most famous working scientist in the country, had an idea for a story about a woman named Ellie Arroway who receives a message from an alien civilization near the star Vega and eventually travels there to make contact. There was a problem sitting right at the center of the plot, and it was not a small one. Vega sits roughly 26 light years from Earth, traveling there and back using anything resembling realistic near-future propulsion. Even something as fast as the Voyager probes would take longer than a human lifetime by an almost absurd margin, closer to 1,000,000 years than to 26. Sagan wanted his character to make the round trip and return within the span of one human life. And crucially, he wanted the physics underlying the journey to actually hold up. He did not want to wave his hands and invoke some vague, undefined faster-than-light drive. He wanted real physicists to read the manuscript and nod along. So he called a friend. His name was Kip Thorne, a theoretical physicist at the California Institute of Technology and one of the leading authorities on general relativity anywhere in the world, a man who would go on, decades later, to share a Nobel Prize in physics for his work on the detection of gravitational waves. Sagan put the question to him directly: was there any scientifically plausible way to cross 26 light-years of space within a single human lifetime without breaking the speed of light? Thorne did not have an answer ready. He told Sagan he needed time to think about it. And for several weeks, he did exactly that, turning the problem over in his mind the way physicists do when a question genuinely interests them rather than merely obligates them. When he called back, his answer was not a faster ship. It was a shortcut through the geometry of space-time itself. It was a wormhole. The mathematical concept of a wormhole was not new even then. Einstein himself, working with a colleague named Nathan Rosen back in 1935, had already described a solution to the field equations of general relativity in which two distant, otherwise unconnected regions of spacetime could be joined by a kind of tunnel or bridge that did not require travelling through the intervening space at all. These came to be known as Einstein-Rosen bridges. But for decades, this idea had remained a mathematical curiosity rather than a serious physical proposal, largely because every version of it anyone had worked out turned out to be catastrophically unstable. The moment anything tried to pass through the throat of one of these bridges, the bridge would collapse in on itself faster than light could ever cross it, crushing anything inside to nothing. Thorne set two of his graduate students, Michael Morris and Ulvi Yurtseva, to the problem of what it would actually take to keep such a bridge open long enough for something to pass through. They published their results in the American Journal of Physics in 1988, and the answer they arrived at required an ingredient with a genuinely strange name: exotic matter. Ordinary matter, the stuff that makes up you, this planet, every star in the sky, has positive energy density, and positive energy density in the presence of a wormhole's throat pulls the throat closed. The same way ordinary matter's gravity pulls everything else toward it. Exotic matter is different. It would need to carry negative energy density, producing a repulsive gravitational effect rather than an attractive one. Line the throat of a wormhole with enough of this exotic material, and its outward push could in principle balance the natural tendency of the tunnel to collapse, holding it open long enough for something or someone to cross. The paper caused a real stir in the physics community, and importantly, it was not because anyone believed a wormhole was about to be built in a laboratory somewhere. Nobody thought that. Nobody thinks that now. We still do not know whether exotic matter with the required properties exists anywhere in the universe in usable quantities, and the engineering challenges involved in manipulating it, even if it does exist, remain almost impossibly far beyond anything humanity can currently attempt. What mattered about Thorne's paper was something quieter and, in its own way, more significant. It demonstrated, with rigorous mathematics, that the equations of general relativity, Einstein's own equations, the ones that have never once failed an experimental test, permit traversable wormholes as a formal solution. The mathematics does not forbid the structure, it simply demands conditions we cannot currently produce. And then, while Thorne and his students were still working through the fine details of stability and geometry, something else emerged from the mathematics, something nobody had originally set out looking for. Thorne realized that a wormhole is not merely a shortcut through space. Under the right conditions, it becomes a shortcut through time as well. The argument runs like this. Picture a wormhole with two mouths, connected by a throat, both mouths initially sitting still, at rest relative to one another, in the same gentle gravitational environment. Now take one of those two mouths and accelerate it to a significant fraction of the speed of light, perhaps aboard a spacecraft, and send it on a journey before bringing it back to rest beside its twin. We already know from the previous part of tonight's story exactly what that kind of high-speed journey does to time. The travelling mouth, moving at relativistic speed, experiences time dilation. Its clock runs measurably slower than the clock attached to the mouth that stayed behind. When the travelling mouth returns and comes to rest beside its stationary twin, the two mouths are once again sitting side by side in ordinary space, but internally they are no longer synchronized. Suppose the stationary mouth has experienced 10 years passing. Suppose the travelling mouth, thanks to time dilation, has only experienced 6 hours. The two mouths are now, in a very real and specific sense, out of step with each other. In time, one of them is effectively sitting 10 years in the future relative to the other, even though they occupy the same location in space. The throat of the wormhole, however, still connects them directly. Step through the stationary mouth, and you emerge from the travelling mouth just 6 hours after it departed. You have made a short walk, physically speaking, and arrived 10 years in your own past. Thorne would later describe this thought experiment using his own wife as the illustrative traveller, a detail he included in his popular writing to make the abstraction feel concrete. She takes one mouth of the wormhole aboard a spacecraft. She accelerates, travels for 6 hours by her own clock, and returns. From the perspective of the mouth left behind, 10 years have passed on Earth. The wormhole still joins them. Reach through from one side, and you can shake the hand of someone standing 10 years in what is, for you, already the past. Step through fully, and you have travelled backward in time by a decade, not metaphorically, not as a narrative device, but as a direct, physically consistent implication of applying general relativity to a structure the theory itself permits. Thorne published these ideas carefully, and he was scrupulous at every step about attaching enormous caveats to them. The requirement for exotic matter remains to this day an open scientific question. We do not know whether negative energy densities exist in nature in anything close to the quantities these calculations demand. We do not know whether a stable, traversable wormhole could ever be physically constructed, even given unlimited time, unlimited resources, and technology centuries or millennia beyond our own. The engineering barriers involved are so far past anything humanity can currently conceive of building that, in any practical sense, they might as well be described as infinite. But there was a deeper concern too, one Thorne himself was careful to articulate, and one that would eventually put him in direct, respectful conflict with one of the other great physicists of his generation. Thorne suspected, though he could not prove it, that the laws of quantum mechanics might quietly conspire to prevent any wormhole time machine from ever actually functioning. He wrote, in one of his own technical papers, that time machines of this kind were likely to self-destruct at the very moment they became capable of operating. His reasoning involved something subtle and genuinely eerie. The instant a wormhole's two mouths fall out of temporal synchronization, the instant it becomes theoretically possible to use the structure to travel backward in time ordinary quantum vacuum fluctuations, the tiny, constant, harmless ripples of energy that exist everywhere in empty space, would begin circulating endlessly around the newly formed time loop. Each trip around the loop, the fluctuations would pick up additional energy, feeding back on themselves, amplifying without limit. Near the throat of the wormhole, that build-up could in principle spike toward infinite energy density, and the wormhole would tear itself apart before anyone or anything could ever actually pass through it as a time machine. Thorne's own equations, in other words, showed him the possibility of a working time machine. His physical intuition told him it was very likely doomed the moment it tried to switch on, but he could not prove that the plug would always be pulled. His mathematics permitted the door. His instincts told him it was probably rigged to slam shut. And that gap between what the theory technically allows and what Thorne suspected physical reality would actually enforce is precisely the gap that another physicist, one far more famous and far more publicly combative on this exact question, decided he was not willing to leave unresolved. His name was Stephen Hawking, and he did not believe the universe should merely make time machines difficult. He believed the universe needed to make them impossible as a matter of principle, and he was going to try to prove it. To make his case, he did something no physicist before or since has ever quite matched for sheer audacity. He threw a party for time travellers, and then he sat down, alone, in an empty room and waited to see who would show up. That party is where we are going next. On the 28th of June 2009, Stephen Hawking hosted a champagne party at the University of Cambridge, in the elegant surroundings of Gonville and Caius College, where he had spent most of his career. The room was prepared properly, the way you would prepare for any celebration. There were balloons tied to the backs of chairs. A pyramid of champagne flutes stood assembled near the centre of the room, filled and waiting. A large banner stretched across one wall, and it read, in plain block letters, "Welcome, Time Travellers." Hawking sat in his wheelchair near the entrance, his eyes tracking the doorway, and he waited. Nobody came. This was not, despite every surface appearance, a party that had simply failed to attract guests. It was an experiment, conceived and executed with the same rigour Hawking applied to every other question he took seriously across his career. The trick, and it was a deliberate, carefully considered trick, was in the timing of the invitations. Hawking did not send them out beforehand, the way you would for an ordinary gathering. He sent them out afterward, once the party was already over, once the balloons had been taken down, and the unopened champagne had gone flat. The invitations included the exact date of the event, the exact time, and the precise geographic coordinates of the venue, specified with a level of detail meant to make the location findable by absolutely anyone, from absolutely any point in history, who happened to possess the means to travel backward through time and read them. The logic behind the experiment was elegant in its simplicity. If backward time travel is ever achieved at any point in the future of our civilization, no matter how distant, then someone from that future should in principle be able to locate a surviving copy of Hawking's invitation, build or acquire a working time machine, and travel back to attend a party that, from their own perspective, had already been publicised as open to exactly this kind of guest. Hawking said afterward that he hoped copies of the invitation would survive for many thousands of years, giving the widest possible window for some future time traveller to eventually find one and make the trip. Nobody came, not that night, not in the years since. Hawking, with the dry, understated humour that characterised so much of his public communication, declared afterward that he now had experimental evidence that time travel is not possible. "I sat there a long time," he said, "but no one came. It is worth pausing here, because there are genuine, serious objections to reading Hawking's empty room as anything close to definitive proof, and Hawking himself was well aware of them. Perhaps the invitation simply did not survive across the centuries required. Perhaps a genuine future civilization capable of time travel operates under some strict, self-imposed policy of non-interference, deliberately avoiding contact with earlier eras precisely to avoid altering their own history. Perhaps, and this is the most theoretically interesting objection of all, time travel of this kind only ever allows a traveller to journey back as far as the moment the very first working time machine was switched on, anywhere in history. Since no such machine existed in 2009, on this reasoning, there was simply no destination in the past for any future traveller to aim for. The party could never have been attended, not because time travel is impossible, but because the party predates the technology that would make attending it possible. That third objection, incidentally, is not merely a clever excuse invented after the fact to save the experiment's dignity. It shows up again and again in serious theoretical work on time machines built from wormholes and rotating structures, and we are going to meet it properly later tonight, because it turns out to place a genuinely hard limit on how far backward any hypothetical time machine could ever actually reach. But the party, in the end, was never really about proving with absolute certainty that backward time travel is impossible. Hawking knew a single null result, however cleverly designed, could never carry that kind of weight. The party was a public, characteristically theatrical expression of a conviction Hawking had already formalized years earlier in 1992 in a serious technical paper. He called it the chronology protection conjecture, and it remains to this day one of the most consequential, unresolved ideas in theoretical physics. The argument runs roughly like this. Suppose you attempt to construct a time machine using a wormhole, following the kind of design Thorne and his students had worked out. At the precise moment the machine would first become capable of functioning a moment physicists refer to as the chronology horizon, something catastrophic begins to happen. Ordinary quantum vacuum fluctuations, the same tiny everywhere present ripples in the quantum fields that fill empty space, begin circulating endlessly around the newly formed closed time-like curve. Each pass around the loop, those fluctuations pick up additional energy from the process, feeding back into themselves, growing larger and larger with each circuit. Very quickly, according to Hawking's calculations, the energy density near the throat of the wormhole would spike toward infinity. The wormhole would not gently fail to work. It would violently destroy itself at exactly the instant it became theoretically usable, before anything or anyone could ever actually pass through it into the past. Hawking phrased the underlying idea in language that has since become one of the more famous lines in modern theoretical physics. He wrote that there appeared to be something functioning almost like a built-in chronology protection agency, quietly ensuring that closed time-like curves can never actually form, and in doing so, keeping the universe safe for historians. A closed time-like curve, to be precise about the term, is simply the technical name for a time looper path through spacetime that begins at one point and, by following the geometry available to it, eventually returns to that exact same point in time. Einstein's equations, as we have already seen through Gödel's rotating universe and Thorne's wormhole construction, do permit such loops to exist under sufficiently extreme conditions. Other mathematical configurations produce them too. An infinitely long, sufficiently massive rotating cylinder, a design proposed by the physicist Frank Tipler in the 1970s. Certain exotic vacuum solutions studied by later theorists. Time and again, wherever physicists have pushed the mathematics of general relativity into sufficiently strange corners, closed time-like curves have kept quietly reappearing. Hawking's conviction was that the universe, in physical practice rather than in pure mathematics, would never actually allow any of these configurations to form. His chronology protection conjecture was his way of formalizing that conviction into a testable physical claim that the laws of physics contain something functioning like an immune system, a mechanism that activates the instant conditions favorable to time travel begin to assemble and destroys them before they can ever complete. There is, however, a problem sitting at the very center of this conjecture, and it is a problem Hawking himself acknowledged openly throughout the rest of his career. He could not prove it. He was able to demonstrate, through detailed calculation, that in many specific configurations, including versions of the Morris-Thorne wormhole itself, the predicted build-up of quantum vacuum energy really would destroy a forming time machine before it could become operational. What he could never do, despite years of effort, was show that this destructive back reaction happens in every possible configuration, under every possible set of conditions, without exception. The chronology protection conjecture remains, to this day, exactly what its name says it is: a conjecture. Not a theorem, an extremely well-informed, carefully reasoned and widely respected guess, backed by real calculation in specific cases, but never elevated to the status of a proven law. And that narrow, stubborn gap between what Hawking believed and what he was ultimately able to prove is where an enormous amount of the most interesting theoretical physics of the last 3 decades has quietly continued to live. Because if Hawking's instinct turns out to be correct in full generality, then backward time travel really is forbidden by the deep structure of the universe, and the door that Einstein's mathematics and Gödel's proof and Thorne's wormholes all leave technically cracked open is, in practice, permanently sealed. But if Hawking's instinct turns out to be wrong, if there exists even one physically realizable configuration where the chronology-destroying feedback does not occur, where the vacuum fluctuations do not build toward infinity in time to prevent the loop from closing, then the door is not merely a mathematical abstraction. It is, in principle, available to be pushed open by whoever eventually develops the resources and the technology to attempt it. For most of the 20th century, physicists assumed that even if some future civilization somehow solved the engineering problem, solved the exotic matter problem, and somehow slipped past whatever chronology protection the universe might enforce, there would still be one more obstacle waiting for them, an obstacle that seemed, for decades, to be the truly fatal one. Not an engineering problem, a logical one. Because even a perfectly functioning, perfectly stable time machine runs headlong into a set of paradoxes so severe that many physicists spent most of the last century treating them as proof, on their own. That backward time travel simply could not be permitted to exist in any coherent universe. Those paradoxes are where we are going next, and one of them in particular is going to take us somewhere genuinely strange, not toward abandoning the idea of time travel, but toward watching modern physicists dissolve the paradox entirely, using nothing stranger than the ordinary mathematics of heat, disorder, and the slow decay of the universe into randomness. For most of the 20th century, even physicists who were personally intrigued by the mathematics of closed time-like curves treated backward time travel as something closer to a logical embarrassment than a serious physical possibility. The reason had nothing to do with energy requirements or exotic matter or the engineering scale of wormholes. The reason was simpler and in some ways more devastating because it did not require any advanced physics at all to state. It could be explained to a curious child in under a minute, and it has been for generations because it sits at the heart of nearly every piece of time travel fiction ever written. It is called the grandfather paradox, and it goes like this. Suppose you build a time machine, or step through a wormhole, or otherwise find your way into the past. Suppose that once there, whether by accident or design, you take an action that prevents your own grandfather from ever meeting your grandmother. Perhaps you delay him at a crucial moment. Perhaps you simply distract him at the one dance where their paths were supposed to cross. Whatever the mechanism, the result is the same. Your parent is never born, which means you are never born, which means, in turn, that you could never have grown up, never have built or found a time machine, and never have travelled backward to interfere with your grandfather in the first place. But if you never interfered, then your grandfather did meet your grandmother after all, which means you were born, which means you did travel back, which means you did interfere. The loop closes on itself and then immediately reopens, forever, with no consistent resolution available anywhere inside it. Physics does not tolerate this kind of contradiction lightly. Self-contradictory physical states are, as a matter of basic logical consistency, not permitted to exist. If backward time travel genuinely leads to unavoidable contradictions of this kind, then something has to give. Either time travel itself is impossible, full stop, or our intuitive understanding of what counts as a genuine contradiction in this context is somehow mistaken in a way we have not yet identified. The grandfather paradox was not the only one troubling physicists who took this subject seriously. There is a second, quieter paradox that unsettles people in a different way once they sit with it, called the bootstrap paradox. Imagine you travel backward in time and hand the complete, finished scores of a great symphonic cycle to the composer who is supposedly going to write it, years before he actually does. He copies them faithfully. He publishes them under his own name as his life's great achievement. Later, in your own present, you learn to play those same symphonies by listening to recordings of performances built directly from the manuscripts he published. Then, on your next trip back, you carry those same scores with you and hand them to him again. He received the music from you. But where did the music actually come from? Nobody composed it in any meaningful sense. It simply exists, circulating endlessly around a loop with no point of origin, information appearing from nowhere and referring only to itself. And there is a third paradox, quieter still, but arguably the most fundamentally threatening to physics as a discipline, because it does not concern grandfathers or symphonies at all. It concerns information itself. Quantum mechanics, in one of its deepest and most carefully guarded principles, holds that information can never truly be destroyed. Every quantum state, every last detail of every interaction that has ever occurred is preserved somewhere in the structure of the universe. In principle recoverable if you had sufficiently complete access to every particle involved. If backward time travel allowed you to alter the past in a way that erased events which had already, in some other sense, occurred, if it let you destroy a piece of information that the rest of the universe had already recorded, and depended upon, then this deep principle of quantum mechanics would be violated, and an enormous portion of modern physics would begin to come apart at the seams along with it. These were not treated for decades as amusing brain teasers to be waved away with a shrug. They were treated as genuine existential threats to the logical consistency of physics itself, and the grandfather paradox in particular was widely regarded as the single most damning argument against ever taking backward time travel seriously as physics rather than as fiction. No matter how cleverly you try to set up the scenario, no matter how elaborate the wormhole or the rotating cylinder or the exotic matter arrangement supporting it, the contradiction always seemed to survive intact underneath the machinery. Waiting, then, in December of 2024, a physicist working at Vanderbilt University in Nashville, Tennessee, published a paper that landed in the small, specialized world of closed time-like curve research like a quiet earthquake. His name was Lorenzo Gavassino. The paper appeared in the journal Classical and Quantum Gravity under a title as dry and technical as physics papers always tend to be. Its implications were anything but dry. Gavassino had done something physicists had been attempting in various forms for roughly 40 years. He had taken the grandfather paradox, the single most famous, most intuitively devastating logical contradiction in the entire subject, and he had shown, using nothing but the standard, well-established tools of quantum mechanics and thermodynamics applied carefully to general relativity, that the paradox simply cannot assemble itself in the first place. Not because some external force intervenes to stop you. Not because the universe reaches in and prevents your hand from moving. Because the actual physics operating inside a closed time-like curve, worked through honestly and rigorously, does not permit the contradictory configuration to form at all. Here is the argument, laid out the way Gavesino built it. Picture a spacecraft traveling along a closed time-like curve, a path through space-time that loops back and eventually returns the traveler to their own point of departure in time. Gavesino asked a very specific, very grounded physical question about that journey. What happens to the thermodynamics of the systems aboard that spacecraft as it completes the loop? We already know from ordinary daily experience that entropy increases. Heat flows from hot objects toward cold ones, never spontaneously the other way. Eggs break and stay broken. This one-directional increase in disorder is precisely what gives time, in our everyday experience, its sense of direction. It is the reason we can watch a film and immediately tell whether it is playing forward or in reverse. The reason we age forward rather than backward. The reason we remember yesterday and not tomorrow. On a closed time-like curve, this ordinary fact runs headlong into a genuine contradiction. As the spacecraft travels along the loop, the second law of thermodynamics demands that entropy inside it continue to increase, exactly as it would anywhere else in the universe. But because the loop is closed, the ship must, by the time it completes its circuit, return to precisely the same physical state it was in when it departed. Both requirements have to hold simultaneously. Entropy must rise throughout the journey, and yet the system must arrive back exactly where it started. Gavesino showed, through careful calculation, that quantum mechanics resolves this apparent contradiction automatically, without needing any additional assumption bolted on from outside the theory. He demonstrated that the energy levels of every particle inside a system traveling a closed time-like curve undergo what he termed spontaneous discretization. Because the loop forms a closed geometric boundary in space-time, the quantum states available to particles moving along it are constrained mathematically to only certain specific, allowed configurations. The same way a vibrating guitar string closed off at both ends is only permitted to ring at certain specific frequencies rather than any frequency at all. This constraint forces the entire physical system to return to its precise initial state by the moment the loop completes. Not approximately. Exactly, to make this concrete, Gavesino modelled what would happen to something simple and well understood, an unstable radioactive particle travelling along such a loop. At first, everything proceeds exactly as ordinary physics predicts. The particle decays the way radioactive particles do. Its components scatter outward. Entropy rises just as the second law demands. But as the system approaches the far end of the loop, where the geometry begins curving back toward its own point of origin, something extraordinary starts to happen inside the mathematics. The decay reverses. The scattered fragments spontaneously reassemble. The particle reconstitutes itself, piece by piece, back into its original form. The entropy that had been steadily climbing throughout the journey begins, instead, to fall. And by the moment the loop closes completely, the particle sits exactly where it began, in exactly the state it began in, as though none of the intervening decay had ever occurred at all. This is not, crucially, a violation of quantum mechanics bolted on as a special exception to make the paradox go away. Gavesino showed it is a direct, mathematically unavoidable consequence of applying quantum mechanics honestly to a system with this specific closed geometry. The reassembly he described is driven by a genuine, well-established phenomenon in physics called Poincare recurrence, a theorem stating that, given sufficient time, Any closed physical system will eventually return to a state arbitrarily close to wherever it began. For an ordinary large-scale system, the amount of time required for this kind of recurrence to occur naturally is almost incomprehensibly long, vastly longer than the current age of the universe. But on a closed, time-like curve, the geometry of the loop itself effectively compresses that unimaginably long recurrence time down to fit within a single circuit. And this is the exact point where Gavesino's work stops being a tidy piece of formal mathematics and starts becoming something genuinely unsettling to sit with, late at night, thinking about your own memories. Because he applied precisely the same logic to memory itself. That extension of the argument, what it means for anything you might remember trying to do on a closed, time-like curve, is where we are going next. Gavesino did not stop at radioactive particles. He pushed his argument one careful step further, into territory that turns the whole conversation from an abstract exercise in thermodynamics into something considerably more personal, and it is worth slowing down here, because this is the piece of tonight's story that tends to follow people quietly to bed. In his framework, memory is modelled the way physics has to model it, stripped of anything sentimental. Memory is a physical interaction. When you remember something, some external event has left a physical trace behind, encoded in the arrangement of matter, in the structure of your neurons, in the wiring of synaptic connections, or, more generally, in any system capable of recording information at all. A photograph is a memory. A scar is a memory. A dent in a fender is a memory. Whatever form it takes, a memory is, at bottom, a pattern imprinted in matter, and matter is exactly the kind of thing the same thermodynamic argument applies to. On a closed, time-like curve, Gavesino showed, any memory accumulated over the course of the loop has to be erased before the loop can complete. The same recurrence that resets the physical configuration of a decaying particle also resets whatever recorded the decay in the first place. If a mind, or any system capable of holding information, is present on that loop, its physical structure gets pulled back toward its original configuration along with everything else. The neurons return to where they started. The traces of what happened along the way are wiped, not by any outside agent reaching in to erase them, but by the same relentless mathematical requirement that pulled the radioactive particle back into its unbroken state. Picture what that actually means, laid out plainly. You step onto the loop, you travel it. Somewhere along the way, perhaps you attempt something the paradox literature has spent a century worrying about. Perhaps you meet your grandfather. Perhaps you pull a trigger, or fail to. It does not matter what you attempt. The geometry of the loop intervenes regardless. Whatever you did, the universe runs its recurrence on the system that recorded the attempt, and by the time you arrive back at the beginning of your own journey, no trace of it remains inside you. The bullet you fired left no mark anywhere in the surviving record. The history you tried to bend springs back, unbent, in every measurable sense. You would not remember any of it. Gavesino himself pointed to something almost poetic hiding underneath the mathematics. Entropy increase, he noted, is the reason we age and eventually die. It is the physical process by which our bodies wear down, irreversibly, moving in one direction only. What happens, he asked, if you invert that process entirely, the way a closed time-like curve requires? The answer, worked out through his equations, is that on such a loop, death itself becomes temporary. Aging reverses, wounds close. Memories dissolve back into whatever configuration they held before they were formed. Irreversible events, the very category of events that define the ordinary one-way flow of our lives, become reversible. Within the small, closed region of space-time occupied by the loop, the arrow of time does not point in a single direction at all. It points in both directions at once, depending on exactly where along the curve you happen to be standing. And with that, the grandfather paradox does not need to be forbidden from the outside, it simply evaporates on its own terms. Not because some cosmic guardian prevents your hand from moving, the way earlier generations of physicists sometimes imagined the universe defending itself. Because whatever you do, the same quantum thermodynamic process that governs everything else on the loop will undo the act, physically, mechanically, and erase every trace of your having attempted it, including the memory that would have let you know you tried. Gavesino's work did not spring up in isolation. It builds directly on a principle first proposed decades earlier by the Russian physicist Igor Novikov, working through these same questions in the 1980s. Novikov argued that if time travel is physically possible at all, only self-consistent histories are permitted to occur. The universe, in his framework, does not stop you from acting. It simply ensures through the ordinary operation of physical law, rather than any special intervention, that every event occurring anywhere on a closed time-like curve fits together without contradiction. Novikov illustrated the idea with a simple mechanical example: a billiard ball. Imagine a ball entering a time machine and emerging in the past, rolling toward an earlier version of itself, apparently on a collision course that would prevent the earlier ball from ever entering the machine in the first place, which would in turn prevent the whole sequence from ever occurring. Novikov showed that there is always available mathematically a self-consistent trajectory instead. The ball does not strike its earlier self squarely. It grazes it just enough to deflect its path slightly, but never enough to stop the earlier ball from continuing on into the time machine. The earlier ball enters, travels back, grazes itself in turn, and the loop closes cleanly. An infinite repeating cycle, but a fully consistent one. No contradiction survives anywhere inside it. Gavesino took Novikov's principle, which had stood for decades largely as an elegant philosophical postulate, and gave it a rigorous physical foundation grounded in quantum mechanics and thermodynamics. He showed that self-consistency along a closed time-like curve is not simply a convenient assumption physicists impose from outside to keep the mathematics tidy. It is a direct mathematical consequence of the laws of physics as we currently understand them. If closed time-like curves exist anywhere in physical reality, paradoxes do not. The universe, on this account, takes care of the bookkeeping automatically. There is an important caveat sitting underneath all of this, and it deserves to be stated plainly rather than glossed over. Gavesino's work does not prove that closed time-like curves actually exist anywhere in the universe. Hawking's chronology protection conjecture might still be entirely correct. The universe might still prevent these loops from ever physically forming in the first place, for reasons unrelated to the paradoxes Gavesino addressed. What Gavesino demonstrated is narrower and more specific. If such loops can form, the physics operating inside them is self-consistent and free of the paradoxes that once seemed to make the entire idea logically untenable. He removed one obstacle. He did not remove all of them. And there is one further detail buried in the framework, the one Gavesino himself has described as the strangest piece of the entire picture, and it is worth sitting with before we move on. He showed that any future version of a time traveller encountered on a closed time-like curve would, at best, be something closer to a statistical echo than a direct continuation of the original traveller, a fluctuation generated by the same quantum recurrence process, rather than the literal same consciousness carried forward and back along the loop. You would not, in any meaningful sense, meet your younger self and recognize the encounter as a reunion. And if some version of a meeting did occur, neither version of you would carry away any memory of it afterward. The universe permits the loop to exist. It strips the loop of any lasting meaning to the people caught inside it. So where this leaves us, halfway through tonight's investigation, is somewhere genuinely strange and worth stating with total clarity. The mathematics suggests that if backward time travel through a closed time-like curve is ever physically achieved, it might not be forbidden by logical contradiction at all. The grandfather paradox is resolved. The bootstrap paradox, worked through under the same framework, resolves in much the same way, with self-consistency enforced automatically rather than imposed from outside. The information paradox, the deep worry that time travel might destroy information quantum mechanics insists can never be destroyed, resolves as well. Because nothing is ever actually erased from the universe's ledger, it simply never gets written into the traveller's memory in the first place. The cost of all this consistency, though, is total. Any meaningful, deliberate intervention in the past becomes impossible, not because the act itself is somehow forbidden, but because every trace of having attempted it is wiped away before the loop can close. You would step off the loop having changed nothing, remembering nothing, carrying no evidence that you had ever left. That single phrase you would not remember is going to return before tonight is finished, because it turns out to describe something considerably larger than the narrow physics of closed time-like curves. But before we can get there, we need to take a detour through something almost nobody expects to find sitting inside a mainstream physics laboratory. Because in 2023, a research team did not wait around for a wormhole or a rotating cylinder or a supermassive black hole to test any of this. They built something far smaller, far stranger, and far more immediate. They built a laboratory circuit that behaves, provably, as though information had travelled backward through its own timeline, and they did it using nothing more exotic than photons and a property of quantum mechanics you have probably heard of without ever suspecting it had anything to do with time travel at all. That experiment is where we are going next. In 2023, a team of researchers led by the physicist David Arvidsson Shuker at the University of Cambridge published a paper in the journal Physical Review Letters that approached the entire subject of backward time travel from a direction almost nobody outside the specialist literature had considered. They did not try to bend space-time. They did not go anywhere near a wormhole, a rotating cylinder, or the mathematics of general relativity at all. Instead, they turned to quantum entanglement, one of the strangest and most thoroughly verified phenomena in all of physics, and asked a deceptively simple question. Could you use it to simulate the effects of sending information backward through time, even if no literal signal ever actually crossed from the future into the past? Arvidsson Shuker illustrated the underlying puzzle with an analogy simple enough to hold in your head as you drift towards sleep. Imagine you need to send someone a birthday gift on day 1. The trouble is, you will not actually learn what they want until day 2, and the gift absolutely has to arrive by day 3. In an ordinary, classical world governed by the everyday flow of cause and effect, this task is simply impossible. You cannot act correctly on information you do not yet have. But using quantum entanglement, correctly engineered, the team demonstrated that you can construct a scenario functionally equivalent to having access to that wish list before it technically exists. Now, it is important to be precise about exactly what this does and does not mean, because it would be easy to walk away from this story having overstated it, and overstating it is exactly the kind of thing this channel tries never to do. This is not literal backward time travel. No information physically travels from a future moment into a past one. Nothing here violates causality in the way a wormhole time machine would, and nothing here lets you send a message to your own past self warning them about tomorrow's lottery numbers. What the Cambridge team actually demonstrated is narrower, and in its own way just as remarkable. Quantum entanglement generates correlations between particles that, under specific, carefully engineered experimental conditions, allow you to extract an advantage in solving certain problems, an advantage that behaves, mathematically and practically, exactly as if information had been sent backward along the timeline, even though at no point did any literal signal make that backward journey. The advantage the team measured is real, it is quantifiable, and it has already found a genuine application. It offers a measurable improvement in certain kinds of quantum metrology experiments, the extremely delicate measurements physicists use to probe quantum systems without disturbing them so much that the measurement itself destroys the information they are trying to extract. The Cambridge result is not a curiosity confined to a chalkboard. It is a working technique, reproducible, published, and already being incorporated into how physicists think about extracting the maximum possible information from fragile quantum states. This experiment sits alongside a second, equally strange demonstration that emerged from a laboratory at the University of Vienna, led by the physicist Philip Walther, working from theoretical groundwork developed by his colleague Miguel Navascus at the Austrian Academy of Sciences. Where the Cambridge team worked with the correlations of entanglement, the Vienna team built something that functions in the most literal sense the language of experimental physics allows, as a rewind button not for a spacecraft, not for a person, but for a single particle of light. The goal Walther's team set for themselves was audacious even by the standards of quantum optics. They wanted to take a single photon, send it through a crystal that would deliberately and irreversibly alter its quantum state, and then reverse that alteration completely, restoring the photon to precisely its original condition. The catch, and the part that makes this genuinely strange rather than merely difficult, is that they wanted to do this without ever measuring or recording what the crystal had actually done to the photon along the way. In ordinary classical physics, undoing a process requires knowing exactly what that process did, so you can apply the precise inverse operation. Quantum mechanics offered Navascus a loophole. Because a quantum particle can exist in a superposition of multiple evolutionary paths at once, and because the order in which quantum operations are applied genuinely changes the outcome, he realized it was possible to design a protocol that placed the photon into a superposition of different paths through a device called a quantum switch, and then used interference between those paths to cancel out whatever the crystal had done, restoring the photon's original state automatically without the experiment ever needing to know what the disturbance had actually been. Navascus described the underlying idea using a comparison almost anyone can picture. In a movie theatre, he said, a film plays from beginning to end regardless of what any individual member of the audience might prefer. But at home, with a remote control in hand, you can rewind to an earlier scene or skip ahead past several scenes you have already watched. That remote control, he said, is quantum physics. Walther's laboratory turned the theoretical protocol into a working experiment. They encoded a qubit, a single unit of quantum information, into the polarization of an individual photon. They passed that photon through a crystal engineered to alter its polarization in a specific, deliberately disruptive way. The photon's encoded information changed, exactly as the crystal was designed to change it. Then they routed the disturbed photon through the quantum switch device built around Navascus's protocol. When they finally measured the photon's state at the very end of the process, its polarization had returned with remarkable fidelity to precisely its original configuration, as though someone had pressed rewind on a recording nobody had ever actually watched. Undoing a disturbance the experiment had never needed to identify or record in the first place. Walther described it afterward as one of the most difficult single-photon experiments his team had ever attempted to build, and the results, once they came in, were unambiguous. The team tested their rewind protocol across a wide range of different disturbances applied by the crystal, varying the nature and severity of the disruption each time, and the rewind accuracy exceeded 95% across the full set of trials. That is not a statistical fluke buried in noisy data. That is a robust, repeatable, carefully verified experimental result published in the journal Optica in 2025. The Vienna team did not stop there. They went on to demonstrate something even stranger sitting on the other side of the same coin, showing that the technique could be used to accelerate a quantum system's evolution as well as reverse it. If you want a physical system to age by 10 years, Navaskas pointed out, ordinary physics insists that it will in fact take 10 years for that aging to occur. You cannot manufacture time out of nothing. To compress 10 years of evolution into a single year of laboratory time, you have to obtain the missing 9 years from somewhere else. The team found a genuine way to do exactly that within quantum systems. They set up 10 identical quantum systems side by side and using their protocol, transferred evolutionary progress from 9 of those systems into the 10th, effectively pausing the 9 donor systems while the 10th system's evolution advanced far beyond what the elapsed laboratory time alone would normally allow. The total amount of evolution across the full set of 10 systems remained exactly conserved throughout the process. Nothing was created. Nothing was destroyed. Time, in the narrow, specific sense physicists mean when they talk about quantum evolution, had simply been redistributed, moved from where it was not needed to where it was. Let's be entirely clear about what these 2 laboratories did and did not accomplish, because the distinction matters enormously, and this channel has no interest in overselling it to you. Nobody sent a spaceship backward through time. Nobody rewound a human being or even a macroscopic object you could hold in your hand. These experiments operate at the scale of single photons and small collections of quantum systems, engineered with extraordinary precision inside carefully isolated laboratory environments. But the implications reach considerably further than the photons themselves. For quantum computing, the rewind protocol carries genuinely revolutionary potential. Quantum computers are extraordinarily fragile, prone to errors introduced by even the smallest environmental disturbance, and existing error correction techniques generally require knowing with some precision exactly what kind of error has occurred before you can correct it. A protocol that can restore a quantum bit to its original state without ever needing to identify what went wrong along the way could, in principle, correct errors faster and more efficiently than any technique currently available. For fundamental physics, the significance runs deeper still. The arrow of time, the fact that time appears, in our ordinary experience, to flow in one direction and one direction only, is conventionally attributed entirely to the second law of thermodynamics. Entropy increases, disorder grows. The past sits ordered behind us, while the future remains chaotic and undetermined ahead. But at the level of the fundamental equations themselves, the laws of physics governing individual particles do not actually require this one-way arrow at all. They are, as we established back at the very beginning of tonight's story, time reversal symmetric. Run the underlying mathematics of a subatomic interaction backward, and it obeys exactly the same laws as running it forward. The arrow of time, at the deepest available level, is not an absolute, unbreakable law of nature. It is a statistical tendency, overwhelmingly likely to hold across large collections of particles, but never absolutely guaranteed for any individual one. The Vienna experiment demonstrates this concretely in a controlled laboratory setting for a single quantum particle. For that one photon, the clock genuinely ran backward. The process was not forbidden by any law of physics. It was merely, at present, impractical to extend to anything larger. Navascus addressed the obvious, inevitable next question directly, and his answer is worth sitting with carefully, because it draws the line between laboratory reality and science fiction with real precision. If you could somehow lock a person inside a perfectly sealed box, completely isolated from every external influence, he said, it would be theoretically possible, in principle, to rewind them using an extension of this same protocol. But with current experimental techniques, the probability of success would be vanishingly small. Scientists estimate that reversing even a single second of a human body's physical existence would require, using anything resembling today's methods, something on the order of millions of years of continuous computation, because the human body contains an almost incomprehensibly vast number of interacting particles, every single one of which would need to have its quantum state reversed, simultaneously and in perfect coherence with every other particle around it. The mathematics, in principle, permits it. The engineering, in any practical sense available to us now, renders it absurd. But the underlying principle holds regardless of how far out of reach the engineering remains. At the quantum level, the arrow of time is a strong suggestion. It is not a commandment. So where does that leave us, standing here roughly 2/3 of the way through tonight's journey? We have watched photons apparently exit a cloud of atoms before fully finishing the process of entering it. We have measured, directly and repeatedly, negative time delays inside carefully controlled laboratory apparatus. We have followed mathematics that shows closed time-like curves, if they exist anywhere in the physical universe, would not tear the logical fabric of reality apart the way physicists feared for most of the 20th century. We have watched a Cambridge team use quantum entanglement to simulate an advantage that behaves exactly as if information had travelled backward along its own timeline. And we have just watched a Vienna laboratory build something that by any honest description deserves to be called a working rewind button for a single particle of light. No one has built a time machine. No person has travelled backward through even a single second of their own life. Every serious physicist working in this field would insist on that distinction being stated clearly. And this channel insists on it too. But the direction the research keeps pointing, again and again, across laboratories in Cambridge and Vienna and Toronto and dozens of other institutions around the world, is unmistakable. And it leads us to a question that sits underneath every experiment, every equation, and every paradox we have walked through tonight. One that every physicist working seriously in this field eventually has to confront directly, without any more mathematics left to hide behind. What, actually, is time? Not how do we measure it, not how does it dilate, or bend, or apparently, under the right conditions, run briefly backward. What is the thing itself? That question is where we are going next. Strip away the wormholes. Strip away the paradoxes and the rewound photons and the empty champagne glasses in a Cambridge dining hall. Ask the most basic question there is, the one a child asks and a physicist spends a career failing to fully answer. What is time? You experience it in every waking moment of your life. It feels like the single most obvious, most undeniable fact of existence, the one thing everyone can agree on without argument. And yet, Physicists, the people who have spent the most careful, most rigorous attention on the question of all, cannot agree on what it actually is. The deeper the tools get, the less certain the answer becomes. The most famous answer comes from Einstein himself, and we have already brushed against it more than once tonight without stopping to look at it directly. In his framework, time is not a separate thing from space at all. It is one dimension woven into a single four-dimensional fabric, space-time. And the universe is not a three-dimensional stage on which events unfold across some independent flow of time. It is, instead, a four-dimensional structure in which every event, past, present, and future alike, simply exists, fixed at its own coordinates. The way a specific location exists on a map whether or not anyone happens to be standing there looking at it. This picture has a name among physicists. It is called the block universe, and it is one of the more genuinely disquieting ideas in all of physics once you let yourself sit with it properly. In the block universe, the past has not gone anywhere. It has not been erased or sealed off or rendered inaccessible in any fundamental sense. Neither has the future been left unwritten, waiting to be decided. Both simply exist, permanently, embedded in the structure of space-time the way every page of a finished novel exists simultaneously inside its binding, whether you happen to be reading page 1 or page 300 at this particular moment. You do not move through time in this picture any more than a book moves through its own pages as you read it. You simply exist along with everything you have ever done and everything you will ever do at a specific location within a four-dimensional structure that was, in some sense, already complete before you ever thought to ask the question. Einstein articulated this view most famously and most personally in 1955 in a letter he wrote just weeks before his own death to the family of his close friend Michel Besso, who had recently passed away. Besso and Einstein had corresponded for nearly the entirety of Einstein's adult life, arguing, discussing, reminiscing across decades of friendship. Now Besso was gone, and Einstein, writing to comfort a grieving family, reached for language that was not comforting in any conventional sense at all. He wrote that Besso had departed this strange world only a little ahead of him, and that this fact, properly understood, meant nothing. People who believe in physics, he wrote, know that the distinction between past, present, and future is only a stubbornly persistent illusion. He was not writing as a poet reaching for something gentle to offer a grieving family. He was writing as a physicist, stating plainly what he believed his own equations had been telling him for 50 years. The man who understood the structure of time better than perhaps anyone else in human history did not believe. At the very end of his own life, that time genuinely flowed in one direction at all. But the block universe, elegant as it is, has a serious problem sitting at its centre, and it is a problem that has never been fully resolved. It does not on its own explain why time feels like it flows, if every moment already exists, permanently, embedded in a single unchanging four-dimensional structure. Why do we experience those moments in a strict, unbroken sequence? Why can you remember yesterday with perfect clarity and yet have absolutely no access to tomorrow? Why does the flow feel so relentless, so one-directional, so undeniably real from the inside if nothing is actually flowing at all? The conventional answer most physicists reach for involves entropy, the same concept that carried Gavesino's entire argument about closed time-like curves earlier tonight. The second law of thermodynamics states that in any closed system, disorder tends to increase over time. Heat flows from hot to cold. Structure breaks down into randomness far more easily than randomness assembles itself into structure. This one-way tendency toward increasing disorder is what gives time in our everyday experience its unmistakable sense of direction. It is the reason you can watch a video of a glass shattering and immediately know, without being told, which way the footage is supposed to be playing. But here is the detail that should genuinely unsettle you. The same detail that has been quietly running underneath this entire episode since the very first part. At the most fundamental level, the level of individual particles and individual interactions, the equations of physics do not actually require this one-way arrow at all. The underlying laws are, as we established at the very start of tonight's story through Feynman's antimatter equations. Time reversal symmetric. Film a single subatomic interaction and play the footage backward, and the reversed version obeys exactly the same fundamental laws as the original. The arrow of time at this deepest available level is not a hard law of nature, carved into the structure of reality the way the speed of light is. It is a statistical tendency, overwhelmingly likely to hold when you are dealing with enormous numbers of particles all interacting together, but never absolutely, unconditionally guaranteed for any individual particle taken on its own. This is precisely why Gavesino's work on closed time-like curves carries such weight beyond its narrow technical result. He showed with rigorous mathematics that on a sufficiently small, sufficiently closed loop through spacetime, entropy really can decrease, locally, without violating any deeper law of physics. The forward flow we experience so completely, so unmistakably, in ordinary life is not some absolute, unbreakable feature woven into the fundamental fabric of the universe. It is simply what most particles, most of the time, in most regions of the universe, happen to do. It is not, strictly speaking, what they are required to do. And there is an even more radical possibility sitting underneath all of this. One that a growing number of physicists working at the frontier of quantum gravity now take genuinely seriously. Some argue that time does not exist at all as a truly fundamental feature of the universe. It emerges the way temperature emerges from the collective motion of countless individual molecules without any single molecule itself possessing a temperature of its own. The Wheeler-DeWitt equation, one of the central equations arising from attempts to combine quantum mechanics with general relativity into a single consistent theory of quantum gravity, does not contain a time variable anywhere within it. The universe it describes is, in a very technical and specific sense, entirely static. There is only a single, timeless quantum state, with no variable anywhere in the equation, marking the passage of moments. So if time is not woven into the deepest layer of reality, where does our overwhelming, undeniable experience of it actually come from? Building on foundational work by the physicists Don Page and William Wouters in the early 1980s, some researchers have proposed that time emerges from quantum entanglement itself, the very same phenomenon the Cambridge team exploited to simulate backward causation earlier tonight. When particles become entangled with one another, the correlations linking them together create an internal structure capable of changing, of evolving, even if the larger system containing them, taken as a whole, remains fundamentally static and timeless. That internal evolution of quantum correlations, on this account, is what we experience from the inside as the passage of time. Time in this picture is generated from the inside out, an emergent property of relationships between particles, rather than an independent stage imposed on the universe from outside. If time really is emergent rather than fundamental, the implications reach further than almost anything else we have discussed tonight. It would mean that backward time travel, understood in the traditional sense of a traveller physically journeying to an earlier point along some pre-existing timeline, might be something closer to a category error than a genuine physical possibility. The way asking what lies north of the North Pole eventually stops being a meaningful geographic question at all. But it might also mean something else entirely, something considerably stranger to sit with. It might mean that what actually matters is not the timeline itself, but the conditions that give rise to the felt experience of time in the first place, and that manipulating those underlying conditions, rather than the timeline they produce, could turn out to be the real frontier, hiding behind everything physicists have spent the last century calling time travel. This is, without any exaggeration, deeply speculative territory. The physics of quantum gravity remains incomplete. We do not currently possess anything resembling a full working theory of everything. We do not know with any confidence whether time is truly fundamental or genuinely emergent. We do not know whether the block universe is the correct picture of underlying reality, or whether something considerably stranger than either the block universe or ordinary flowing time turns out to be true instead. But here is what we do know with real confidence, standing at this point in tonight's story. Our intuitive, everyday picture of time a river flowing steadily in one direction, a clock ticking at the same universal rate for everyone, everywhere, an absolute unchanging backdrop against which all events simply unfold, is wrong. Einstein proved this more than a century ago, and every experiment conducted since, from Haffel and Keating's atomic clocks circling the globe on commercial airliners to Scott Kelly's slightly younger heart returning from the International Space Station, has only confirmed that he was right. Time is flexible. Time is relative. It passes at genuinely different rates for different observers, depending on how fast they are moving and how deep they sit inside a gravitational field. And at the quantum level, the level Feynman's antimatter equations first cracked open for us at the very start of tonight. Time can, under the right conditions, run backward, reset itself, and behave in ways that violate almost every assumption our ordinary daily experience quietly trains us to believe without question. We are not, standing here, at the end of this story. We are, if anything, closer to its beginning. The question of what time actually is, and whether its flow can ever genuinely be redirected rather than merely reversed for a single isolated photon in a laboratory in Vienna, remains one of the deepest open questions physics has ever asked itself. And there is one more question left to ask tonight, a question that is not, in the strictest sense, purely scientific at all, a question that is, instead, quietly and unavoidably human. If backward time travel does eventually become possible, in some form, at some scale, for someone, somewhere, far beyond anything we can currently build, should it ever actually be used. That is where we are going next. Part 10. What you would carry back and what you would not. Imagine for a moment that everything tonight's story has described actually works. Imagine the wormhole holds, the exotic matter exists in sufficient quantity, Hawking's chronology protection turns out, somewhere somehow not to apply. Imagine the lever is real and it is within reach. Where would you go? What would you try to change? The instinct, when people actually sit with this question rather than treating it as an amusing hypothetical, is almost always the same. Fix something. Prevent a tragedy. Warn someone before the moment that changed everything. Undo the specific instant that still, years later, sits lodged somewhere in your memory like a stone you cannot put down. That instinct is not foolish, and it is not shallow. It is one of the most deeply human impulses there is, born out of love and grief and the quiet, constant knowledge that time moves in exactly one direction and takes everything you have ever cared about along with it, whether you are ready to let it go or not. But everything we have walked through tonight suggests that changing the past, even if the physics somehow allowed you to reach it, might not work anything like the way that instinct imagines it would. Gavesino's mathematics, the mathematics that dissolved the grandfather paradox back in part 7, showed that a closed time-like curve enforces self-consistency automatically, without exception. You cannot create a genuine paradox on such a loop, not because some external force reaches in and stops your hand, but because the combined mathematics of thermodynamics and quantum mechanics conspires, quietly and completely, to ensure that whatever you do gets undone again before the loop can finish closing. Your actions, on this account, are erased. Your memories of having acted at all are wiped clean, folded back into the same recurrence that resets everything else the loop touches. You return to where you began as though nothing had ever happened. You would not remember. That phrase deserves to sit with you for a moment, because by the time you reach the end of a story like this one, it stops being only a technical description of a physical process happening somewhere out at the edge of theoretical physics. It starts to sound like something considerably closer to home, something about your own relationship to your own past. Because here is the quiet truth underneath everything tonight has covered. Even without a wormhole, even without a rotating cylinder or a spinning black hole or a single exotic particle of negative energy matter anywhere in sight, the person you were 10 years ago is already, in every operational sense that actually matters to you tonight, sitting on a closed time-like curve you cannot enter. You can think about them. You can turn the memory over, examine it from every angle, ache over it in the dark. But you cannot walk back into that room and meet them. You cannot warn them. And even in the strange hypothetical world where the physics somehow allowed the meeting to occur, Gavesino's mathematics suggests the encounter would be erased before either version of you could carry a single lesson forward out of it. You would not remember. There is a related idea, quieter but just as unsettling, called the Novikov self-consistency principle. The same principle we met back in part 7 through the billiard ball that grazes rather than strikes its earlier self. If you could genuinely travel to the past, Novikov's framework suggests, you would not actually be changing it at all. You would simply be participating in the version of it that already, in some sense, always included you. The bullet you fired would miss, not through some improbable stroke of luck, but because the geometry of the loop never allowed it to hit in the first place. The warning you shouted would somehow go unheard. The letter you finally worked up the courage to write would arrive one day too late, through some chain of circumstance neither you nor anyone else could have predicted in advance. Not because the universe is cruel, because the loop was never anything other than fully, seamlessly consistent with the history you already remember living. There is one more possibility worth laying out honestly, because it offers something closer to hope, even if it is a strange and imperfect kind of hope. The many worlds interpretation of quantum mechanics suggests that every quantum measurement, every fork where multiple outcomes are physically possible, actually produces a new branch of reality rather than collapsing down to a single result. If some future version of time travel worked by this logic instead of Novikov's closed loop logic, then travelling backward might not return you to your own personal past at all. It might instead deposit you into an entirely new branch, a parallel timeline running alongside your own, in which the tragedy you hoped to prevent genuinely does not occur. Your original timeline, the one you actually came from, the one holding every memory you still carry, would remain completely untouched, unaffected, exactly as it always was. This is not redemption in any way that would feel satisfying if you sat with it honestly. It is not healing in the sense that word usually implies. It is duplication. The suffering you hope to erase would not vanish from the universe. it would simply continue to exist, unchanged, in the timeline you actually inhabit, while an entirely separate version of events, involving people who are not, strictly speaking, the same people you lost, plays out somewhere else, in a branch you yourself will never get to visit or confirm. And then there is the loneliness, because every single ancient story tonight's script has quietly been building toward every version of this exact narrative that human beings have been telling each other for thousands of years, long before anyone had the mathematics to describe why it kept happening, carries the same underlying shape. A traveller leaves the ordinary flow of time behind for what feels to them like only a brief interval. They return to find that the world around them has aged far beyond anything they were prepared for. Everyone they loved is gone. These stories are not, underneath their surface details, really about physics at all. They have always been about loss, about the specifically human terror of being left behind by time, or of leaving everyone else behind without ever intending to. Scott Kelly came home from the International Space Station 8.5 milliseconds younger than his twin brother. That difference is completely undetectable, invisible to any measurement short of a sophisticated atomic clock. But now imagine the effect scaled up, the way we imagined it back in part 3, to something you could actually feel. Imagine travelling at 99% of the speed of light on a genuine journey to a nearby star. From your own perspective, the round trip takes only a handful of years. From Earth's perspective, meanwhile, decades pass in your absence. You return to a world that has quietly moved on without you. Colleagues have retired. Old friends have died of ordinary old age. The culture has shifted in ways you were never present for and cannot fully catch up on. The specific buildings you remember, the small, unremarkable landmarks that anchored your sense of home, are simply gone, replaced by things that mean nothing to you yet. You have not, in the dramatic, cinematic sense, travelled through time at all. You have simply lived your life at a different rate than everyone else around you, and the price of that difference turns out to be everything you once knew, gone quietly while you were somewhere else, living what felt, from the inside, like an ordinary handful of years. The psychological cost of genuine, meaningful time dilation may turn out to be the cruelest part of this entire subject, crueler, by far, than any of the logical paradoxes we spent part 6 carefully working through. Not the grandfather paradox, not the bootstrap paradox, the grief. The specific, quiet grief of coming home to find that home no longer quite recognizes you, and that you no longer quite recognize it either. And yet there is something else sitting inside these stories too, something beyond the loss, something every culture across every era of human history seems to have independently recognized and folded into its own version of this same tale. Time is precious specifically because it passes. Moments matter specifically because they end. Love carries the particular urgency it carries precisely because it is temporary, because it cannot be paused, rewound, or held indefinitely in place while you decide, at your leisure, whether you are ready to let it move forward. The arrow of time, the strict, one-directional flow from past into future that has run underneath every part of tonight's story, is not, in the end, a curse laid on us by an indifferent universe. It is the very thing that gives any of this weight in the first place. If every moment simply lasted forever, available to revisit and revise whenever you wished, no single moment would ever have mattered quite as much as it does now, tonight, passing while you listen to this. Einstein believed the distinction between past, present, and future is only a stubbornly persistent illusion, and he may well have been correct. The block universe may genuinely be the true underlying structure of reality. Every moment you have ever lived may, in some sense, still exist somewhere within the four-dimensional fabric of space-time, your earliest memory, your first day at a new school. The specific face of someone you loved and eventually lost. None of it, on this account, is truly gone. It is simply located at a different coordinate within a structure that has already, in some deep sense, always contained it. But we do not experience the block, we experience the flow. And whether that flow is fundamental to the universe or merely emergent, whether it is objectively real or, as Einstein insisted, a persistent illusion generated somewhere inside consciousness itself, it remains, for all of us, the single most human thing there is. It is the quiet tick of the clock on your nightstand tonight. It is the sound of your own breathing, slowing, as you read or listen to these words in the dark. And it is, whatever else it may secretly be underneath, the only version of time any of us will ever actually get to live inside. We have spent tonight walking a very long hallway, and it is worth pausing here near the end of it to remember every door we passed through to get here. We began with a phone call between two physicists in 1940, and an idea so strange it sounded almost like a joke that unravelled into one of the most rigorously tested symmetries in all of physics, the discovery that antimatter and backward moving time are mathematically the same object wearing two different names. We stood beside a mathematician handing his closest friend a birthday present that quietly troubled him for the rest of his life. A solution to Einstein's own equations describing a universe where the geometry itself would let you climb into a spacecraft and land precisely in your own past. We flew commercial jets loaded with atomic clocks around the entire planet and watched time disagree with itself by measurable fractions of a second. We followed a novelist's phone call to a theoretical physicist at Caltech all the way to a wormhole, and then watched that same wormhole quietly reveal itself to be a door through time as well as a door through space. We sat in an empty room in Cambridge, waiting alongside a man in a wheelchair for guests who never arrived, and we took his experiments seriously even as we examined honestly every reason it might not mean quite what he hoped it meant. We followed a young physicist at Vanderbilt through the mathematics of closed time-like curves and watched him dissolve, with genuine rigour rather than hand-waving, the single most famous paradox in the entire subject, only to discover that the price of that resolution is total, complete forgetting. We read stories from India and Japan and Ireland and the Middle East, composed by people who had no equations at all, who nonetheless arrived, through pure narrative instinct, at structures that look, when you set them beside modern physics, disturbingly precise. We watched a laboratory in Vienna build something that deserves, without exaggeration, to be called a rewind button for a single particle of light, and a team in Cambridge demonstrate an advantage that behaves exactly as though information had travelled backward along its own timeline, even though nothing, strictly speaking, ever did. And underneath every single one of those stops along the hallway, the same quiet, patient question kept resurfacing, refusing to be fully answered no matter how far we pushed. What is time, actually? Not how do we measure it? Not how does it bend or dilate or, apparently, under sufficiently strange conditions, run briefly the other way? What is the thing itself, underneath all of our descriptions of its behaviour? Here is what tonight leaves you with, honestly, without inflating it into more certainty than the physics actually supports. The equations do not forbid backward time travel. They never have. From Feynman's positrons, to Gödel's rotating universe, to Thorne's wormholes, to Gavesino's self-consistent loops, Every serious mathematical framework we have built to describe the deep structure of reality leaves the same door standing very slightly ajar. Nobody has ever found a clean, rigorous, universally applicable proof that slams it permanently shut. Hawking believed such a proof existed, waiting to be found, and he spent real effort trying to find it, and he came away only with a conjecture, however carefully reasoned, rather than a theorem. That gap between conjecture and proof has now stood open for more than 30 years, and it remains open tonight, right now, while you listen to this in the dark. But the door being unlocked and the door being walkable through are not the same thing, and tonight has tried, at every step, to be honest about that distinction rather than blur it for the sake of a better story. Every theoretical time machine physics has ever proposed the rotating cylinder, the traversable wormhole, the spinning black hole requires either exotic matter we have never detected, energy densities no civilization we can currently imagine could produce, or engineering scales so far beyond anything humanity has ever attempted that the word difficult barely applies anymore. The gap between what the mathematics permits and what human hands could ever actually build remains honestly almost incomprehensibly wide. It may always remain that wide. Nothing in tonight's story should be mistaken for a prediction that any of this will happen. To you, to your children, or to any civilization descended from either of you. What tonight's story is instead is something quieter and in its own way stranger to sit with. It is the discovery that the question of backward time travel is not, and has never really been, a question confined to science fiction. It is a question that keeps showing up, uninvited, inside the ordinary working mathematics of extremely serious, extremely careful physicists who were, in most cases, not even looking for it when they found it. Feynman was not trying to invent time travel when he worked through Wheeler's strange phone call. He was trying to understand antimatter. Gödel was not trying to build a time machine when he sat down to honor his friend's 70th birthday. He was simply refusing to leave any corner of Einstein's equations unexplored. Thorne was not chasing backward causation when Carl Sagan called him about a novel. He was trying to help a friend solve a plot problem involving the ordinary forward passage of time across interstellar distances. Again and again, across nearly a century of research, backward time travel has arrived as an uninvited guest at the edges of investigations that were, on the surface, about something else entirely. That pattern, more than any single result on its own, is what should stay with you tonight. There is a particular kind of humility worth carrying away from a story like this one, and it is worth naming directly before we close. It would be easy, hearing everything tonight has laid out, to walk away either wildly overconfident that time travel is coming, or dismissively certain that none of this matters because nobody will ever actually build the machine. Both of those reactions miss the point, and both of them miss what is actually interesting about where physics currently stands on this question. The honest position, the one every physicist named tonight would recognize and largely agree with, sits somewhere quieter, in between. We do not know whether backward time travel is physically possible. We know it is not logically forbidden in the way earlier generations of physicists confidently assumed it had to be. We know the paradoxes that once seemed to end the conversation permanently have, in careful modern hands, dissolved into something considerably stranger and more subtle than outright impossibility. And we know that every year, in laboratories scattered across the world, from Toronto to Vienna to Cambridge, physicists keep finding new, small, carefully controlled ways to make time behave just a little less obediently than we were ever taught to expect. That is not a small thing to know, even if it never resolves into a working machine in your lifetime or in any lifetime that follows yours. It changes something quiet about how you are allowed to think about the past. Not because you will ever get to walk back into it. You will not. Nothing in tonight's story offers you that, and nothing honest ever could. But because the past, according to some of the most careful mathematics human beings have ever produced, may not be quite as sealed off, quite as permanently gone as your ordinary daily experience insists it has to be. It may simply be very, very far away, sitting at a different coordinate inside a structure that, in some sense, physicists are still arguing about, has never actually stopped existing at all. There is one part left in tonight's story, and it is the shortest one, and it is not really about physics anymore. It is about you, lying wherever you are lying right now, at this particular coordinate, on this particular night, and what it might mean to hold everything we have covered gently rather than anxiously as you finally let yourself drift off.